Hello everyone, welcome to lecture 19. This is machine learning from data, and this video we will, in fact, in this entire lecture, we'll talk about something that's known as unsupervised learning. Of course, we've talked a little bit about it in some of the earlier lectures, but today we are going to take a better look at the important aspects of unsupervised learning. In specific, we will talk about k-means clustering, probability density estimation, and Gaussian mixture models. Just like before, first, let's recap quickly what we did in the previous lecture. So in the previous lecture, we talked about something that's known as radial basis functions. We looked at the non-parametric ones at first, and these we found were the extensions of the nearest neighbor, such that we were weighing the data points depending on their location with respect to the test point. And then eventually we summed up the impact of each one of those to get the final hypotheses. Again, similar to the nearest neighbor, we did not require training of the data. All the benefits of the nearest neighbor came with it, simple to implement, simple to understand. But then it also came up like it comes with its set of drawbacks that are similar to the nearest neighbor, which was that the high computational cost exists because then we are working with the entire data set. And based on that, like because we had these drawbacks, we came up with something that's known as the parametric K radial basis function network eventually. And we began by deriving the parametric radial basis function, which essentially was created by having bumps or curves over every data point, which was like obviously different from the non-parametric one. And then based on that, we decided to have some parameter called height, and based on that, its contribution on the test point is ascertained. Once we had that, the final hypothesis was nothing but a linear model. As you can see here, this was my final hypothesis, which was nothing but a linear model, which was all good news because the moment we come across linear models, we know how to solve them. So the final hypothesis was a linear model with features that can be replaced by some representative parameters. One of them was the centers of in the data, the clusters that we talked about. And then in some sense, the model became non-linear in these centers because we didn't, if this exists as it is, then this is non-linear because like we have missing parameters that are the weights and then this mu j. But then we figured that in some sense, we can get rid of the non-linearity because we do not directly use them in the sense that we come up with just by looking at the data distribution, we come up with these centers. And so in a certain way, we saw we took a peek at unsupervised learning. And then finally, we looked at the impact of regularization depending on the value of k. There was a relationship between k and r. And here, as you can see, the white one is the target function. The blue one is the fitted one, with just like k equals 4. So k is the number of clusters, obviously. And then as we increase the number of clusters, you can see the amount of this is the regularized version, but we saw the unregularized version where there was a lot of overfitting, but with a little bit of regularization, we could see that we got almost a fit that was k equals 4, but then we are not losing the flexibility of our complex model. That was the fundamental idea behind using regularization with parametric k radial basis function network. All right, so having recapped this, today we are talking about unsupervised learning. Unsupervised learning is by definition, we are trying to find patterns or organization within the data because we are not using the labels that we've been using until now. So this is we don't have the answers. A very sort of simple way of understanding it is that until now we had x's and y's, and based on this y, we were making some decision on something that was unknown, a new x, for instance, or x prime. But now in unsupervised learning, we don't have that. So that's the definition, I would say. And we try to derive patterns, and based on that, we try to get answers to some x prime that is unknown. Now we have seen unsupervised learning, a little bit of it from two contexts before. The first one is pre-processing to organize the data for supervised learning. If you remember, the branch and bound to make it more efficient, tight and well-separated clusters is the requirement. And that is organizing data for a faster nearest neighbor search, right? So there we saw a hint of unsupervised learning in the sense that we were trying to derive some information by organizing data in a certain way. And then determining the centers for the RBF bumps that I just talked about in the previous lecture, where we were setting the centers based on the distribution of the data, right? Determining the centers for the bumps that we needed. So unsupervised learning has this role to play in data organization for my supervised learning problem, right? But it also has, in addition to this, it also has a very important role to play in the basic learning problem itself. It's useful on its own, right? So that's what we're going to focus on in today's lecture. It's important to be able to organize data to identify patterns. For example, we can learn patterns from like the language before even knowing the language, right? Just by listening to the language, you can derive certain patterns without really knowing the rules behind them. But because of the usage, you can tell that this is what this means, right? So that is the fundamental idea behind unsupervised learning. Let's look at this example that we looked at earlier, but now more from the perspective of what we are going to do today, right? So if you look at the picture on the right, this is clustering, and this is clustering with 10 clusters, which means we created 10 clusters. This whatever we are going to apply, that we will obviously talk about. Let's say we applied unsupervised learning. It came out with this 10 clusters of data that almost correctly classified most of the digits, because we had like these 10 digits, right? And we did not have the actual labels, which means we did not know which digits are which. And again, the features that we're using is like symmetry and average intensity. So with the 21 nearest neighbor, the advantage that it had was that we can do multi-class classification, right? So because we have like 10 of these, 10 classes. But in this case, we didn't have but of course we had labels here. We knew that this is 1 and this is 2 and so on. But we didn't have that. And if you just compare each of them, you see that we are able to form these 10 clusters with like such a good structure, which is almost similar to my supervised learning, which is on the left side. This reveals the power that unsupervised learning can offer in situations like these. For instance, a lot of data, multi-class classification. Well, go with clustering instead of getting labels, because it might be computationally challenging. So we're going to see all of that. We're going to discuss all of that. And in general, we'll discuss clustering, develop techniques and algorithms. And if you think about it, clustering in general is a hard problem. So it's not something that is easy to achieve, because just with 10 clusters, you can tell like these are 10 different classifications. So getting the intricacies from the data is not that straightforward. And so let us define the problem and start working as to how do we like achieve this. All right, so let me define the problem. Clustering is a technique, is one of the unsupervised learning techniques. So unsupervised learning techniques, right? And what is the problem that we have at hand? The problem that we have at hand is that I have this data set that, as always, has some input, let's say xn. And the problem as such is defined that the outcome that we want, or the output that we want for any unsupervised learning problem, is that I need to I need to finally be able to cluster data into some subsets, right? Into some subsets based on whatever criteria, right? So what we have is this D. We do not have the Y values. We do not have the labels, right, from the data. Or maybe because if we chose to use unsupervised learning techniques, we chose to ignore the Y values. We don't have them, or we just decided we want to get some information from the data based on the distribution of the data. And so we don't want to use the labels. So now one question is like, we want to cluster data into some subsets. So then the question arises like, we need to know how many, right? Otherwise it doesn't make any sense. So how do we come to know how many? So we need to know how many, and that is what we have to come up with, right? And by the way, this is like an open research question on which a lot of research is still being published. And there are different ways of like how many clusters, optimal number of clusters for a given problem, and so on. But we're going to look at some basic ideas that accompany this problem in general, right? So assuming like we need to know how many are required, and then only we can like cluster data into certain subsets. So let us assume we are given this like number of sub. For now, we are going to assume, and let me write it down. Assume we are given like k subsets. Okay, so I'm given k subsets. Let me begin with that, right? So essentially my output is going to be something like this, like k subsets of this data D, S1, S2, and so on up to Sk. So I'm just like calling these subsets S sub I. Okay. Now, fine, I have this input. The output that I want is these k subsets, but then how do I get these k subsets, right? Even if I'm given that I need like, let's say 10 clusters, how do I get these 10 clusters? So what we have to do is we'll simplify the problem and develop some criteria to finally achieve these clusters, right? And first of all, we need to do like this criteria has to do with the clusters themselves. Like what exactly are these subsets? What exactly are these clusters? So let's like define certain things that are required by these subsets. So the first thing that's required when we're talking of clusters or when we're talking of these subsets is that these should be non-overlapping, or in terms of like mathematics, you can say that these are disjoint. All right, so that means non-overlapping. What does that mean? That means that these they do not intersect. There is no common element in each one of them. Of course, practically that's next to impossible to achieve, but for theoretical purposes, we can assume that in practice there's always an overlap, and then there are ways to deal with it. For example, we can define a separate cluster for the overlapping region. That's one like way to deal with it. Of course, like if we have more clusters, we'll have more overfitting, and you know the issue with overfitting, and so we have to come up with something in between. But my point is that we assume that this is what we want. This is what we want to achieve, right? Of course, practical considerations aside. All right. The second thing is that clusters must be complete. That means they will, and I'll write it down, complete. These subsets or these clusters should be complete. Well, what does that mean? They should cover the entire data set. Nothing should be left out. Entire data set. That this is what this means. They should cover the entire data set. Nothing should be left out. Well, the first thing that comes to our mind is, what about outliers? So there might be that one outlier because of which I have to create like one whole cluster. Again, there are enhancements or modifications that are available to deal with that. But then again, we'll stick with this assumption that like we are considering the simple assumption that they are complete and disjoint. So then only we'll be able to define these clusters. And once we have this definition intact, then we will develop more theory around that to solve this problem, right? First, formulate the problem and then solve this problem. So that's why I'm sticking with the assumption that these are disjoint. And so mathematically speaking, I can write this as something like this. So S sub I intersection S sub j, right, is empty. Doesn't have anything. And I is, of course, not equal to j. That's the first mathematical sort of definition. The second point that we raised, that they have to be complete, means the union of like I equals 1 up to k S sub I is the data set itself, because we define the data set here, right? So this is what we want to achieve when we are talking about, I would say, clusters. Now this, like these two criteria, they seem trivial, right? They seem trivial to achieve because we can just like randomly generate some k clusters anyways. And so I can have like all of them complete and then disjoint as well. So what else is required to make this problem non-trivial? Because there has to be something in addition to this that makes it relevant to my machine learning problem as such, right? And so we have to think in terms of like we have thought about things on those lines when we were talking about the branch and bound. In branch and bound, what made my clustering good, if you remember, right? Let me use another slide. So what makes clustering good in general? That's my question now. What makes clustering good in general? Think about it. And as I said, in branch and bound, we talked about it. So the first thing that makes it really good is that the points within a cluster should be as close to one another as possible. So tightly bound, right? Tightly bound within cluster. And the second thing that made it really good was that these clusters should be as far from, like, well separated, right? As far from one another as possible. So points in different clusters should be well separated. Well separated, which meant this between clusters should be high, or like should be enough, the between cluster distance, right? So these two criteria ensured that we get good clusters. Now, mostly when we look at what we are going to derive just now, we focus on the first criteria, but then the second follows, and we'll see how, right? So, like focusing on the first criteria, we define a clustering error. So what is this clustering error? This clustering error will be defined for every cluster, and that is going to be in terms of the distance of every point from the center. Think of, like, we have these S1, S2, and so on, SK clusters, right? And each one of these has like some centers because these are like almost circular, right? And this, like mu sub j for each of these, like mu1, mu2, mu3, it has this distance from every point x in that cluster that belongs to that cluster. And we are going to mathematically define it or denote it, first of all, as E sub j. So think of this as the sum of squared distance to the center, right? And let me not write an arrow here. Instead, let's write it equal to what it is. Okay, so this is equal to, like, for any point xi within, and then I'm like saying, okay, and then sum up the distances. So I'm saying each of these xi's belong to S sub j because I'm calculating it for the cluster j. And then the center for cluster j is mu j and squared, right? So as I said, sum of squared distances to the center. So this is essentially also telling me how large is this cluster. The larger the cluster, the more you'll have this. And so this is like an error measure, which maybe signifies the spread of my cluster, right? The spread of cluster. All right. So what do we need then? Because we started with saying that we need some kind of a criteria to take care of like these 2 points, making a good cluster. Now I have this error definition for one cluster, and like, think about it. If this is small, that means I am meeting the first criteria. If this E sub j is small, then my clustering is good. And for like, and I need it for all the clusters. So essentially the overall error for this clustering problem is going to be the sum of all of these j's. So that is from j equals 1 up to k, if there are k clusters, E sub j. So now if we have this E that is like really, really small, if my E is really small, then I can come close to the fact that my clustering is good, right? Because I have like this close tightly, because think about it, this actually becomes, and now because this is for all the clusters and xi is like point in that cluster, it could be like in general any data point in my entire data set. So I'm like replacing these two summations. In fact, they get replaced by these two, by the entire data, right? So here my E is going to be xn minus mu, and then I'm writing it as a function of like xn because it's like this, the center to which this xn belongs. It's the center of that cluster to which this belongs, essentially. Good, right? So this is for all data points. Xn is any data point within my data, and then this is the center of the cluster to which xn belongs, this mu. All right. So this thing here, this E equals this term here is known as the k-means clustering error. So let me write it down. This is the k-means clustering error. And this is that criteria that's going to tell us how good our clusters are, right? So again, think of it as the sum of squared deviations from the center. And then we already talked about it how. Our goal, what is our goal now in the clustering problem? Our goal is to find subsets and corresponding centers which minimize this error, as always, right? Every machine learning problem is nothing but an optimization problem that's trying to minimize some form of error, and we try to formulate that in this problem. Center for each cluster, so again, like what is the criteria? First of all, like the center for each cluster has to be well defined, like corresponding to each point, because then that comes in my equation, right? And also because like every data point belongs to a cluster, so that's going to point number one in our criteria, right? Tightly bound. And then, sorry, it comes to like point number two, because if each data point belongs to a cluster, then that's covering like the entire data set, right? So basically I'm talking about these points, complete and disjoint. So this covers like the second part where it covers the entire data set. And then point number one, a data point cannot belong to more than one cluster, right? And so that's why they are disjoint, because like somehow we have to make sure that this data point has this center only, and so that's how I'm going to calculate the distance. So both these 2 points essentially here, disjoint and complete, are covered by this definition of my error. So it's like pretty intuitive in that sense, and this is known as the k-means clustering error. All right, so having defined, just like always, having defined error, now we want to know how can we solve this optimization problem, because this is an optimization problem where we are trying to minimize this error for my entire data set. All right, so let's try to understand that. And so what do we want? That's the question that we should be answering. Well, we want to output clusters, right? So let me say I want to output S1, S2, and so on up to Sk, right? And each one of them should have like mu1, mu2, and mu k centers. And remember when we began discussing this, we said we already have this k, right? But if you think about it, this problem is really hard to solve computationally. In fact, so much so that it's an NP hard problem. Okay, what is an NP hard problem? Well, some problems that are extremely hard to solve, computationally challenging, cannot be solved completely. And so we have like heuristics to come close to maybe optimal. We cannot reach the optimal. For instance, we have seen one like another NP hard problem. That's the linear model classification that minimizes the E in. So basically getting the number of mistakes to zero. So essentially for problems like these, we have to build a heuristic, as I said, that gives a solution, a very good solution, but not optimal, because then it's NP hard and there is no way that we can get to the optimal. All right. So for this one, for this problem, to minimize the clustering, the k-means clustering error, what we do is we use something that's known as the alternating algorithm. That's also the Lloyds algorithm. So alternating algorithm, also known as Lloyds. Of course, we've seen that name before, but Lloyd's algorithm help us solve this problem as well. Okay, so this is it's a very intuitive algorithm. So according to this algorithm, what we are saying is we know that we cannot solve this problem given it's NP hard, impossible to get to the optimal. But in general, if we have something given to us, right? So the first thing is if I have centers given to me, mu1, mu2, and so on up to mu_j, if these are given to me, if I have the centers essentially, then we know how to solve this problem greedily, right? Maybe if I'm given some centers or maybe I'm given optimal centers, I don't know. But if that's a given, if that's an input to me in some ways, then I can solve this problem greedily and get good results, of course. Okay, so let's see how that is possible. Now, each center, if I'm given that center, will represent a data point. So I will take a data point and assign it to this center that is closest, right? So let's say I have these data points here, and I have like these are my centers, not data points, and data point could be something, some other points around them, entire this thing. And let's say these are the centers that are given to me. I should draw them like more bold. Right, so you know that we can, like, each of these centers in the space corresponds to a Voronoi region. And so we can draw Voronoi regions around these. And once we have them, we know that like every data point belongs to one of these regions, right? And so maybe I'm bad at drawing that, but looks somewhat like this. and so on, right? So essentially all data points, like let's say there was this x of n belongs to this region. So it's essentially assigned to the region where this center lies. So it's easy to see that this is going to be an optimal solution. And of course, maybe let's say there was one more here, right? So you can tell by looking at these regions that we just created that we can like get an optimal solution by definition, because the distance from any data point xn, right, is closer to its center mu n, let's say this is my mu n, than any other center because it lies in that Voronoi region. So this will minimize the distance between my xn and mu n, and that is what my goal is, right? If, of course, this criteria is met, then I can get this, and I can get the optimal. All right. What is the second criteria in this alternating algorithm? And by the way, we are just like developing the criterias. We haven't come to the actual algorithm as such. And so the second is that if you give me subsets, so let's say S1, S2, and so on up to Sk are given, or Sj, Sk, right? Sk are given, and this is also K, why to confuse, right? If these are given to me, then I can construct the optimal centers easily. Why? Because it's related to the fact that we are looking at the squared errors. We already know which data points are in each subset, right? And because of the squared error, it's easy to construct the centers because of the clusters of the subsets. And if we weren't using squared error, it might be harder. But now that we have like the definition of the error itself as a squared error, so we can like get the centers that minimize this E sub j. Let me show you what I'm talking about. My Ej, if you remember, was something like this. Any x belonging to S sub j, x minus mu j squared, right? So whatever optimal like center I'm looking for, let's say that optimal is mu sub j like star, this is going to be the mean, right? The optimal center is going to be the mean. So essentially mu sub j star is going to be x belonging to S sub j. The sum of these, like the mean data points in S sub j divided by like this cardinality, the number of points that are there, right? So this is the second criteria. If like I'm given these, then I can construct like these optimal centers for every subset. That's what I'm trying to say. Okay, so with these points, this like point number 1 and point number 2, like these help us construct this like alternating algorithm that's known as the Lloyds algorithm. Let's see how can we do that, right? So Lloyds algorithm. Okay, step 1, find the centers like in a given data set. So go and find these centers, mu1, mu2, and so on up to mu k. Now the question arises, how do we find them? I mean, you just said that like either one of them like either the centers have to be given or the subsets have to be given. I don't have anything. Well, because if it's the beginning of the algorithm, just like randomly choose some data points, right? So that's how you begin. They're usually randomly selected, and there are better like criteria to obviously get a good start. But just like randomly chosen data points, that's fine. Or you can do like as the like the centers could be the mean vector in the respective clusters S sub j. Either way, it's fine. So or like the mean vector in S sub j, we just saw because like most likely, I mean, if we have some information around that, we can get the means and begin from there. But mostly it's like if it's the beginning, then it's the randomly chosen point. But then once we have that, like step number 1, step number 2 is assign data to centers greedily. What does that mean? Assign data to centers, these centers that we just chose greedily. Okay, so how do we do that? Let's say I have like this data point xn, then we find like the distance of that, like the center which minimizes the distance to xn, right? So basically what we're trying to solve is this kind of a problem at every step. Arg min xn minus mu j squared, right? So assign it depending on whichever is the nearest, right? And then based on that, solve this problem. Okay, xn belongs to mu j or mu k, I don't know which one, but anyways, like based on this solution, I'll decide, right? Okay, so beginning with these two steps, I will get some kind of partitioning into a subset, right? And so next, what I should do is keep repeating this step again, because the centers are going to like change, because I just began with some randomly selected ones, right? And so again, go back, repeat step one until convergence. Okay, so repeat until convergence. Okay, so then the question arises, when will convergence happen, right? And how do we know that the algorithm has converged? Now, in each step of the algorithm, if anything changes, it's because the error is strictly improving. Okay, so let me write it down, like about convergence. If we are noticing some kind of change, that means my error is improving, or it's going down, right? So improving most likely. And why is that? For example, like if we have to move a point from one cluster to another, that means that the center is closer now because the earlier center wasn't as good, right? And so this is strictly going to decrease my error E. So that could be one. The other scenario could be that if any of the centers is not the corresponding mean, because that's what we said, right? Either it has to be like the mean, the center has to be the mean, or we have to like do some changes and then update the centers, right? So if any of the clusters is not the corresponding mean, then by moving the center to the corresponding mean, you're strictly improving the error again. So in either case, we are improving the error, and each of the step is strictly like each step is decreasing this error. Each step is decreasing this error. All right. And well, there are only a finite number of clusters, and error cannot like go on decreasing forever. So eventually the algorithm converges after some finite number of iterations. All right. We can at times get the issue of local minima that happens depending on the data distribution. And so we are not guaranteed optimal all the time, but we do get a good solution in this algorithm. And this is known as, again, I'm repeating, Lloyds algorithm. All we have to do is begin with some randomly selected centers and then assign data greedily. And maybe like in the next step, because this could be randomly selected when this is the first step. And then the next time we can get the centers by calculating the mean vector in a certain cluster. And so these will get updated maybe in the next iteration, and then keep assigning data to centers until convergence. All right. So in the next video, I'm going to stop here. In the next video, I'm going to show you some examples of this algorithm in action. So let's move on to that.